Hi, and thanks for tuning in to the CBA Podcast, a place where we chat about our own recent achievements in the area of electronics, software and mechanical engineering, and more likely than not, give excuses for not having done anything at all. Hello and welcome back to yet another episode of the CBA Podcast. For your benefit, and for your information, I re-recorded this whole episode because it was getting too boring. I was just rambling on and it was becoming a boring pile of crap. So you're welcome. Now, we got some feedback from our own trustful quality reassurance team saying that my voice is too soft in comparison with the little jingle in between segments. So the jingle was loud, my voice was soft. Now, I'm going to try two things. Speak up a little bit and also make that jingle a little bit less loud. So let's see if that works out. That was better, right? No problem. Now we're almost halfway into 2019 and at the start of this year I made some New Year's resolutions, as I'm sure many of you did yourselves. And just for fun and maybe to make you feel better about your own New Year's resolutions that you may have kept, let's go through them and see what became of them. First of all, I was going to read the news only once a day. Yeah, that didn't work out really well. Read the news multiple times a day, mostly to postpone actual work. Next thing, I was going to do more sport. Yeah, it worked out pretty well. I'm doing a lot and it feels super cool. Next thing, I wasn't going to watch random YouTube videos anymore, just watch videos from a few channels I'm subscribed to. No, it didn't really work out very well. I watch a whole lot of videos and it's becoming a bit of a mess. Next up, I wasn't going to have Twitter open all the time in the background, only check it a few times a day. Yeah, that worked out pretty well. Only check it about 3 times a day, maybe a little bit more depending on what I'm expecting. So that worked out nice. Next up, I didn't want to have Gmail chat or Gmail open all the time, just check it a few times a day. No, it didn't really work out that well. When everything is normal, I have it open all the time, so yeah. Next up, I wanted to put my phone on vibrate or even completely sound and motionless, only visual indication that somebody calls, and leave it in another room and don't take it with me when I go somewhere. Yeah, it worked out pretty well. So if you call me and I don't pick up, I'll see your call. I'll mail you back. No worries. And finally, I was planning on reading a book instead of watching endless YouTube videos when I was going to sleep. No, it didn't really work out at all. I watch a buttload of videos and it's becoming a bit of a problem, so I'll have to work on that. So there you go. About 50% of all New Year's resolutions turned out fine and I'll call it a win. Something I actually did, already talked about it a little bit last time, was make a small inline PCB for general purpose use. It's a long PCB, about 1.5 centimeters thick, 6 centimeters long. It has a microcontroller on there, SD card slot, push button, 1 output signal buffered to 30 milliamps, approximately 1 input signal, open drain and with a pull up, 1 LED and 1 3.3 volt LDO, so you can input, let's say 5 volt or 6 or 7 until 10 or 12 or something like that maybe, and pull 3.3 volts out. The microcontroller works on 3.3 volts as well. Of course, there were a few failures with this PCB, as there are failures with most PCBs here. First of all, I put a 14 megahertz crystal on there, and the microcontroller itself is an Atmel or microchip now AVR. It's running at 3.3 volts. Now, the device is only spec'd until 10 megahertz running at 3.3 volts, so I'm not even using the crystal, I'm using the RC oscillator. So I ordered some slower crystals, 8 megahertz crystals, to replace them, but I just might leave it like this, it works fine. Another thing is, although there's a relatively big LDO on there, SOT223, with a relatively big heatsink and a copper plane as heatsink, the tracks leading up to the LDO and coming from the LDO are way too thin to carry 1 amps. The thing is rated for 1 amps, but no way you can pull 1 amps through these little tiny tracks, so let's not do that then. But the thing itself works quite nice. I use it here to make a light effect for a wall clock lamp. Stuck some LEDstrip around the wall clock, made some software to display a round circular light effect thing. It works quite nice. Put a PCB behind the clock so it's small enough to be tucked away. And that worked quite nice. I use the same PCB and basically the same software to make a light effect at the heck-a-lot space at the underside of a coffee table to brighten up the place a little bit. And I'll put videos, or at least links to videos of both of these things in the show notes if you're interested. Powering a LEDstrip, I ran into a quite interesting problem. Now, my setup here is I chose a wall wart power supply, fixed power supply. I had that controller PCB that I just talked about, and I have a light source, in my case a LEDstrip. Now, if software in my case runs correctly, the total current pulled by the light strip is less than the maximum current of the power supply, so everything is fine. Voltage is stable, everything is cool. However, if I make a software bug, in this case I made a bug related to timing, I think, to drive the LED data stream out. What happened was all the LEDs go into full brightness, full white, and the total current pulled by the LED source, the light source, is much more than the power supply can deliver. So what happens is the power supply voltage drops, typically, and drops below the brownout voltage of the microcontroller. So now you have a system that when you power it on, the LEDs go into full brightness, the voltage of the power supply drops, and the microcontroller is kept in reset. So basically you have a system that you cannot flash anymore. There are some ways around that. You can disconnect the light source or feed the microcontroller, power the microcontroller separately from the light source, but maybe the easiest is to either build in a small delay of, let's say, 1 or 2 seconds between the microcontroller boot and the actual light effect starts, or make it so that if you press a push button or hold some pin high or low during startup, that the light effect is disabled. So, because else what you have is a system that you can plug into the wall and immediately it goes into overdrive or overload and you cannot flash it anymore. So what you want is a way to interrupt that. So I learned a little bit from that. I hadn't really given it much thought until now, and it's a very practical, very real problem, I think. Now, something software related that may be of interest to you. For all microcontroller stuff here, basically all microcontroller stuff, I use AVR microcontrollers. Atmel AVR or now Microchip AVR microcontrollers, and use AVR GCC, which is an AVR port of the GCC compiler toolchain, and use AVR libc, I think it's called. It's a common standalone C library for microcontrollers. So in this light effect I just described, I use some randomness because I didn't want to include a random table in EEPROM or something like that. I just wanted a random effect, so that was the easiest. So this C library provided a rand function, which basically spits out a 15-bit random number. And I never used it until now because I thought it was quite slow and quite unpredictable, so the execution times of the random generator varied very much according to where you were, I guess, in the sequence or something like that. I'm not too smart to know exactly how it works, to be honest, but it does some measurements here. So the execution time of the rand function in the C library, and it took about 800 to 844 cycles, that is 100 microseconds at 8 megahertz. Two things I found interesting was that it's relatively fast, so 800 cycles is not a whole lot, and also the variation is quite small, so 800, at least 800 and at most 844 cycles, so around 100 microseconds, so it's quite predictable actually. So that's I think I'll use it again. It's much easier than using a precompiled random table in a EEPROM or something like that. So that was nice. Of course, your microcontroller rand implementation or your C library may vary, so this is what I use. So one final thing I want to talk a little bit about, relevant for everyone I guess at some point, is voltage drop in cables. It's not rocket science. If you have a length of cable and you run a current through it, there will be a voltage drop between the point where the current enters the cable and exits the cable, let's say that. Typically, if you have a power supply connected to a load, connected to load by a cable, through a cable, you have one strand running to the load and one strand returning from the load, the plus and the minus, let's say that. So 10 meters of cable, in quote marks, is actually 20 meters of single core cable. So I did some calculations and measurements. Let's see what the voltage drop was in cables, just to give an idea. Let's say you run 1 amp through cable. That's a typical current for a LED effect, I guess. If you have relatively big cable, it's 0.75 millimeters square. You can use about 10 meters of cable to cause a 0.5 volt drop. And I guess 0.5 volt is the amount of voltage drop that you can tolerate in your application. Guessing. Right, so 10 meters, 0.75 millimeters square, 10 meters of cable at 1 amp, 0.5 voltage drop. If you have a ridiculously thin wire like 0.14 millimeter square, you can only use about 2 meters of cable between your source and your load for a 0.5 voltage drop at 1 amps. So that's much less. So don't expect great results using 10 meters of garbage cable or thin cable or junk cable. What I used for this effect that I just described at the Heckelot, I think, was about 5 meters of 0.5 millimeter square cable. And what I actually measured was 0.5 voltage drop at 1 amps when using a little over 5 meters, so that's fine. I guess calculated and measured numbers differ a little bit depending on the construction of the cable. So if you have multi-core or stranded cable, I'm not sure exactly what they call it, the resistance is probably a little bit higher than when you have solid core with a given diameter, I guess. Maybe also interesting is I had a 5 meter LEDstrip with WS2812 LEDs and just running a random effect. And what I did was measure the end of the cable, so at a single feed point where the power came in at one end, and I measured at the other end of the cable what the remaining power was. In other words, what the voltage drop was in the cable. And I recorded the minimum voltage that I measured. So over some time, an effect that ran for some time, I measured 3.8 volts, so that's 1.2 volt drop over a 5 meter LEDstrip. And the current was, the average current was about 0.7 amps. So just to give you some numbers, right, what to expect. So don't expect great results when you have a 10 meter LEDstrip running a very heavy effect and only feeding it at one point. So that's not really going to work. You need 2 feed points or multiple feed points for that. Not exactly rocket science, but I tend to skip this stuff or forget this stuff when I'm in a hurry or I'm not really interested in what I'm doing. I use junk cable and then I'm surprised by the voltage drop over that cable. And then finally, one upcoming event is the Maker Faire in Eindhoven. And although the Maker Faire itself is 28 and 29 September, the closing date for application, if you want to be there and show your projects or whatever, is June 30. So if you want to participate, make sure to give them a call before June 30. They might extend the date, I guess, but better safe than sorry. So that was all for now. For more information, links and previous episodes, visit podcast.cba.si. Stay tuned, thanks for listening, and goodbye.